This is our last segment on buffers, 15.1 through 15.3. Remember, a buffer is a weak acid in its conjugate base or a weak base in its conjugate acid. Just going back to a buffer solution from the time before, HF breaks up into equal amounts of, or let's say we have an equal amount of HF, which is a weak acid, in its conjugate base, NaF, F minus being the conjugate base. What happens is the pH will equal the pKa plus the log of the base over the acid. And because the base and the acid are the same, pH equals the pKa, which equals 3.14, and that's all you need to do to solve the problem. If you have unequal amounts of the weak acid and its conjugate base, you can use the Henderson-Hasselbalch quite easily. You figure out your moles or molarity of HF, the molarity of F minus right here, and notice it's going to be pH equals pKa plus the log of the base over the acid. So it's 3.14 plus the log of 0.20 over 0.25 gives me 3.14 minus 0.10, which gives me 3.04. So with a little bit less base than acid, your pH is a little bit lower than 3.14, which makes it 3.04. So the point of a buffer is if you add a strong acid to it, the strong acid like H plus gets absorbed by the F minus and gets converted to a weak acid such as HF. And then pH isn't affected so much. Or if you add a strong base to it, the strong base takes the HF and converts it to F minus, which doesn't have as much effect on the pH as OH minus would. So F minus affects the pH more than OH minus. So let's take a look at the example we did here with the 0.50 liters, 0.50 molar, and 0.50 liters, 0.40 molars of NaF. And now we're going to add 0.030 moles of NaOH to it. What's going to happen is we're going to add some of the HF will get converted to F minus, and we end up with, starting with 0.25 moles, we lose 0.03 moles of that, it becomes 0.22 moles. And the 0.20 moles, we add 0.03 moles, and it becomes 0.23 moles. And now we can plug it into Henderson-Hasselbalch. Notice we have a slightly more conjugate base than acid, so we get 3.14 plus 0.02 gives me 3.16. Let's flip the page here and see if this thing lines up here. Looks like we're good to go. And let's see, what if, now this time we add 0.030 moles of HCl, assuming it's not going to affect volume much. We take the 0.25, add 0.03, which gives me 0.25. We take the 0.20, subtract 0.03, which gives me 0.17. Why did we add or subtract the 0.03? When we added the acid, what happened? The F minus, the HF got, or the F minus got converted to HF, so we have more acid and less of the conjugate base when we do that. So the HF increases, the F minus decreases. Plugging in, we can just say pH equals the negative log of 3.14 plus 0.17 over 0.28. We get 3.14 minus 0.22, 2.92. Still not a very large change in pH. What about weak bases? How does that work? It's going to work much the same way as the acids did. I'm going to start out with NH3 in this problem. I'm going to add water, do the hydrolysis equations, forms NH4 plus and OH minus. And notice it's a common ion effect. I got 0.40 here, and I got 0.30 of NH4 plus here. So what's going to happen is the NH4 plus is going to kick equilibrium this way, lowering the OH minus. In other words, it will be less basic than expected if you just had the NH3 present. Now you can solve this through KB or using the Henderson-Hasselbalch, but I'm going to go right to the adjusted Henderson-Hasselbalch, this one down here, which is really the way to go, and it's the easiest one to do. So I do POH is the PKB, which ends up being 4.74 because it's the negative log of the KB. And then I take the log of this base, it's log of the acid over the base. So when you're doing the Henderson-Hasselbalch with the POH form, it's the log of the acid over the base, and that's the conjugate acid, which is 0.30 molar NH4 plus over the base 0.40 mole NH3. So I divide that through, and I ultimately get minus 0.12, and the 4.74 becomes 4.62. Now remember, that's a POH, so if I subtract that from 14.00, I get a pH of 9.38. What happens, it's a buffer solution, what happens if I add NaOH to it? Well, the NaOH is going to get absorbed by the NH4 plus, converting it to a weak base, NH3. So it's going to raise the pH, but not as much as expected, because the NH4 plus is going to absorb it, converting it to NH3. And here's an example of how that works. The NH3 goes from being 0.40 plus 0.05 moles, gets to be 0.45. NH4 plus starts at 0.30 but loses 0.05, goes down to 0.25. I plug it into the POH version of the Henderson-Hasselbalch. I get 4.74 plus the log of the acid over the base. I minus 0.26. I get the 4.48, that's the POH, and a pH of 9.52. Notice I added a base, so it raised the pH from the original amount. The original was a 9.38, now it's 9.52. What if I added acid to the original amount? Again, I add the strong acid. Now the NH3 absorbs the acid and converts it to NH4+. So it's not going to have the effect of adding straight H+. It's like adding NH4+, which doesn't affect it as much. The 0.40 minus 0.05 becomes 0.35. The 0.30, I believe that would be plus 0.05. It's supposed to be, would become 0.35. And notice we're going to use the POH version of the Henderson-Hasselbalch, 4.74 plus the log of equal moles of acid and base. Just means that's going to turn out to be 0. So my actual POH is 4.74, making my pH 9.26. Okay, because I added acid, it actually lowered the pH from the original 9.38. So those are some examples with Henderson-Hasselbalch equation. The big advantage of using that, you can work with it in molarity, or you can just work with it in moles like we did, because all we have to do is know the mole ratio of the acid to its conjugate base or base to its conjugate acid. Thank you.